Welcome back to the second part of my little introduction to the ASP solving process. My name is still Thorsten Sharp and I'm still using the graph coloring problem to illustrate the overall process. Okay, in the first part I've been giving you an overview over the process. I've introduced you to the problem of graph coloring and introduced you to how problems are modeled in ASP. The first thing is actually that problems are normally decomposed in two parts. For one, the problem instance, in our case the graph, and for the second part, an encoding that allows you to solve all problem instances of this class in the same way. That is actually the encoding. The other thing about the encoding is that it works in a generate and test fashion, at least the methodology for writing things down. So you write a generator that generates all solution candidates and a tester that filters out the valid solutions. Well, I think you all know this by heart right now, so let's come to the fun part, which is actually grounding and solving, and let's start with grounding. First of all, let's make sure which Gringo version I'm using. Actually, Gringo 4 on my machine is simply a link to the currently installed Gringo version. With -- version, we know now that it's Gringo version 4.4. Okay, now let's start grounding. Let's look at the human readable output of Gringo. So we can get this by adding the option --text to the call to Gringo. And otherwise we have here the problem instance, an encoding of our graph, and here the actual problem encoding that represents the problem of graph coloring. Now launching this gives us this ground program, and ground because it contains no first order variables. Let's just see where this starts. And now it'll be interesting to see actually where the different parts come from, how they relate to the original encoding.
So we look at the representation of our graph as well as the encoding of graph coloring, the actual problem class we are looking at. Here we go. Now, first thing the grounder actually spits out is the edge predicates, the instantiation of this. Well, there's nothing to instantiate because the facts were given as such here in the problem instance. So next we see here the three colors, red, green and blue, which were actually contained in here. So you see the order really doesn't matter in that sense. The grounder parses both files together and builds them up accordingly, starting with all the facts. And now here, well, a little modification has been happening. The range here from 1 to 6 has been expanded, and we have here the 6 facts, one for each node. Now the next interesting thing are actually the integrity constraints here, and they stem from instantiating this constraint here, this integrity constraint. Now let's take a closer look. Actually, if we look at the first 3, they all originate from instantiating this integrity constraint for the edge 1, 2. This one. So we instantiate x and y for 1 and 2, but then we have 3 different possibilities for the coloring, for the C here and the C here, and these are all the 3 we have up here, and this then results in 3 integrity constraints, and these are the ones we get. Now one thing that is perhaps interesting to observe is we only get here the atoms dealing with coloring, but not the atoms dealing with the edges, which we have actually here, but that is this guy here, or the instantiation of this guy, edge 1, 2, has been removed. Well, it has been removed because we know already the truth value of it. We know that it's true because it's given here as a fact. This is different from these guys here, from the color atoms. It is, for instance, we do not know that 1 is to be colored with red or 2 is to be colored with red. This has to be determined by the solver, and hence they cannot be simplified. They are passed to the solver. Now the next interesting thing actually is to see what happens actually to this cardinality constraint.
The instantiation of the cardinality constraint can be found at the end of the output, and here actually the first thing we can observe right away is that each cardinality constraint is translated into a count aggregate. So more or less we count the true atoms in the set and have to make sure that in the end the cardinality of them equals 1. Finally, the instruction to the solver, show color, is just passed through and dealt with the solver in the end. Okay, now let's look at this from a machine-readable perspective and see what happens if we launch the grounder but do not use the human readable output, and let's look at the format that actually the solver has to understand. The machine readable output of Gringo is actually given in the so-called S-models format. This is named after the solver S-models. That was the very first ASP solver, which itself relied on the grounder LPAS, and they used this format as their intermediate language, and we rely on this as well. Now, to get this machine readable output, you launch Gringo as we did before, just without the option ---- text, and the default behavior then is the output of the ground program in the S-models format. Now, if you look at this format, the first thing that strikes the eye is it's full of integers, and this is of course the very idea of this format. All atoms, that is all ground literals, are expressed as integers and also represented as such in the solver, actually, as a side remark. Now, the key to understanding this actually is to look at the first digit in each line, which is here the number 1. Because each digit identifies a type of logic programming construct, and there are actually several primitive ones that we can look up briefly in looking at a table in our book. This table summarizes the different types of rules that are supported in the S-models format. Now, normal rules are the simplest one, and they all start with a 1 in the S-models format. 2 stands for cardinality rules, and 3 for choice rules. And these are actually the 3 types of rules that we also observe in our little examples. Otherwise, we have wait rules, minimize statements, disjunctive rules, and whatever is there yet to come. Coming back to our example, we observe that most of the rules are actually normal rules. Here we have a 1, and this continues actually down there. A closer look, however, reveals that the first group of rules, these guys here, they are all facts. The second group of rules are actually the integrity constraints, except that they have a dedicated head atom, which is a symbol that is always evaluated to false. Now, afterwards we have here a choice rule, then 2 cardinality rules, and this group here we will actually have 6 times, because each group of 3 represents 1 cardinality expression in the original encoding. The decomposition, or let's say the normalization of such cardinality constraints into a choice rule and 2 cardinality rules is described in the book, and I cannot go into further details in this very shallow introductory text. Now, at the end of the program rules, we have a separator. This is here this 0 on a single line, and this separates the program from the symbol table. The symbol table here puts in correspondence the original atoms, say color 1R, with its representation as an integer, in this case 28. Now you may wonder what happened to all the other symbols, like about nodes, about edges. Actually, we have put them aside by telling the solver to project on the instances of the binary color predicate. Let's look at this again. You see here, we say, show us only the instances of the binary color predicate, and accordingly, only those instances are contained in the symbol table. There's more to say, but I will not go into details right now, so let's go back and continue with solving. Before computing the stable models of the obtained ground program, let's make sure which version I'm using. As before, we do this with the option ---- version, and in my case I'm using class version 303. Now all this is about the workflow, and I think this is nicely represented by this statement here. We have a program encoding, which is this guy. We give it together with a representation of the problem instance to Gringo, and the result is piped into Clasp. If we just launch Clasp as is, it will compute one stable model, also called answer set. And here it is. This answer set is represented by the projection on the binary color predicate. So we color 1 with green, 2 with blue, 3 with blue, 4 with red, 5 with green, and 6 with red. Otherwise, the example is very, very simple. As you see, the timer didn't even react to it. Everything is just instantly. Another thing that is interesting to observe actually is this little plus symbol here, which Clasp uses to say, I stopped after my search after the printing these answer sets, in this case only one, but there may be more. So if one wants to have all answer sets, one simply adds a 0 at the end, and this gives all answer sets. As you see here, there is no plus left, so the search space has been exhausted, and we get altogether 6 answer sets. If you want less answer sets, you can just, let's say we want 3 of them, specify so, and then again the plus symbol appears to indicate that there may be more answer sets. Although I'm not going to detail it here, simply because our example is too easy, let me point out the option stats. So if you launch class with this option, you get statistics, not only about the original program, but also about the search. Again, search was so easy, it's not worth really commenting on it. In our case, where we may have a look actually is, this is the number of original atoms, the number of original rules, the number of different bodies, which is actually smaller than the number of rules. Then we learn a little bit more about how the workflow actually works in more detail. There's actually some pre-processing going on, equivalence pre-processing. Here in this easy case, already 87 equivalences were detected, 31 among atoms or negations of atoms, so it may find out that A is equivalent to not B, and hence remove, for instance, B from the solving process and replace not A at its position. Then there were no equivalences between bodies, and other equivalences, perhaps between atoms and bodies, or other artificial variable that appeared. Anyway, so 87 equivalences is not so bad given that there are only a little bit more than 100 rules. The program is tight, which means there is no positive recursion. And in the end, what the solver receives after pre-processing are 24 variables and 57 constraints. So from the 131 rules, only 57 constraints are induced. And among them, and this is very typical for ASP problems, there are more than 80% of binary variables, 10% of ternary ones, and some other ones. So this high number actually of binary variables is due to a transformation happening because the logic program is treated by the so-called Clark's completion. But this is just as some background information. Okay, that's it about the solving process. Now let me just make some miscellaneous commands before wrapping up this video. Clingo is actually a combination of Gringo and Clasp, and the acronym stands for Clasp on Gringo. Okay, first of all, let's make sure which version I'm using, and this will also show us the versions of the underlying systems. So here I'm using Clingo version 4.4, and this version always follows the version of the underlying Gringo version, or vice versa, depending where the innovation is. And this is here combined with the Clasp version 3.03. Let me just point out some little details. I guess the most interesting option of all the systems is the help option. And to be honest, there's a lot of information. This is actually why Clasp, Gringo, and Clingo have different levels. So if you launch Clingo with the option help, you get help on all different systems. So here you have the Clasp config options, the Clasp solving options, ASP options, Gringo options, and other basic options. And if you want to learn a little bit more about this, then you should launch the whole thing with option 3 and you get more details on it. So as you see, there's much more to learn about, and perhaps we will learn this in another video in the future. But despite all these options, Klingo allows us to simplify our workflow in a little way. So before we were launching Gringo and Clasp on our problem with a Unix pipe, so we launched it like this. Now we can do the same thing in Klingo, just with a single system. So we have Klingo 4, and this will automatically call in the grounder as well as the solver. So we can do it like this and get the same result. What I found funny is the option mode. Is you can also run Klingo as if you were running Gringo or as if you were running Clasp. So this is actually the same as we did before by launching Gringo and then piped it into Clasp, just that we launch Klingo in different modes. And again, we get the same results, at least hopefully. Anyway, I hope you enjoyed this video. It was my very first video on ASP, and well, I hope you tolerate the little flaws here and there. And I hope to get more of them out in the future, at least if there are not too many grumpy people who dislike them. Okay, have fun and enjoy, and stay hungry, stay foolish.